Happy learning! Today we're going to talk about concavity and points of inflection. Okay, so what is concavity? Concavity tells us which way the curve is bending. All right, so if our curve is bending like a smiley face, the concavity is concave up. So the curve is concave up if it's bending like a smiley face, or even just part of a smiley face. And if it's part of a frowny face, it's concave down. All right, so the concavity tells us how the curve is bending. And we could get the concavity from the second derivative of the function. All right, and so this theorem, it says the function f is concave up if f double prime of x is greater than 0. All right, so if the second derivative is positive, our curve will have this sort of shape. Okay, so maybe it's just the left part of it, maybe it's the right part, maybe it's the whole thing, but we'll determine that later. But the second derivative being positive tells us that we're concave up. Similarly, it is concave down if, well, you guessed it, f double prime of x is negative. All right, so if our second derivative is positive, our curve is concave up. If our second derivative is negative, our curve is concave down. A point of inflection is a point on the graph where the curve changes concavity. So this means that the curve goes from concave up to concave down, or vice versa. And so if our curve changes concavity, we say that point is a point of inflection. Okay, you experience points of inflection all the time when you're driving. If you drive, a point of inflection occurs when your steering wheel changes from pointing to the left to pointing to the right. When it's pointing straight for that moment, that's going to be a point of inflection on the road. So how about that? All right, and so to find points of inflection, that's when our second derivative is 0 or undefined. So the second derivative will be 0 or undefined at points of inflection. So to find the points of inflection, we're going to have to find the second derivative and find when it's 0 and find when it's undefined. Those are going to be some candidates for where the points of inflection could be. Those values might not all be points of inflection, but some of them might be. Okay, so this is for finding points of inflection and concavity. So the first thing we're going to do is we're going to find the second derivative. All right, so we're going to take two derivatives of our function. We're going to find when it's 0. Or find when it's undefined. Okay, this is going to give us some x values. but it's a point of inflection. It's not an x of inflection. It's a point of inflection. It has an x and a y. So we're going to use the original function to find all potential points of inflection. So that's going to give us the y values. So we're going to use f of x to find all potential points of inflection, not just the x values. Okay? And then if f double prime changes signs, at this point, a point of inflection occurs. All right, so it's as simple as that. So let's take a look at an example. Let's find all points of inflection and concavity of the graph of f of x equals x to the fourth over 2 minus x to the third plus 5. All right, so here we have this function x to the fourth over 2 minus x to the third plus 5. We want to find all points of inflection and also when is the graph concave up, when is the graph concave down. And so what do we need? We need both derivatives. So f prime of x, that's the derivative of our function. We bring the 4 in front. That's 2x to the third minus 3x squared. The derivative of 5, as you know, because you are a boss at this point, is 0. And now we need the derivative of this function. Bring the 3 in front. 6x squared minus, bring the 2 in front. 6x. We want to find when this is 0 or undefined. It's a polynomial. It's never undefined. Okay, so let's set this equal to 0. We could factor out a 6x. And so our candidates for the points of inflection are 0 and 1. Use our function to find all potential points of inflection. Let's get these as points. F of 0. Subbing 0 into our original function, we get 5. So 0, 5 is a potential point of inflection. And then we sub 1 into our function. When we sub 1 into our function, we get 4.5. All right, so these are both potentially points of inflection. And so what we're going to do now is we're going to take our number line, right, let's take the number line. We're going to break it up at 0, and we're going to break it up at 1. We're going to take a test point in each of these intervals and check, is our second derivative positive or is our second derivative negative at each of these intervals. All right, so our test points could be -1, 0.5, and 2. F double prime of -1. That's a negative times a negative. Negative times a negative is positive. Okay, so on this interval, we're concave up. f double prime of 0.5. That's a positive times a negative. That's a negative. On this interval, we're concave down. And f double prime of 2. That's a positive times a positive. A positive times a positive is a positive. All right, so we go from concave up to concave down. That means point of inflection at the point 0, 5. And then we go from concave down to concave up. We got another point of inflection. So in this example, both of our candidate point of inflections turned out to be actual point of inflections. Okay, so if a special case, like why do we care about points of inflection? If p of x is the profit function, all right, so if we have this profit function, the point of inflection is called the point of diminishing returns. Why is this? Because it is where the rate of return goes from increasing to decreasing. Right? The derivative of our profit would go from increasing to decreasing. So the amount that our profit is increasing by is slowing down. So it's the rate of, or it's the point of diminishing returns. Okay, so you will see points of inflection discussed in like a business or an economics class, but it might be with this term instead, the point of diminishing returns. But you know that it's just a second derivative. Okay, so let's take a look at an example. So suppose our profit function is negative 0.2 x to the third plus 3x squared plus 6. I want us to find the point of diminishing returns, or diminishing value is what it's also called. Okay, so how do we do this? We want to find the points of inflection on this graph. It's as simple as that. So we need the second derivative. But to get the second derivative, we need the first derivative. All right, so how do we get the first derivative? We bring the power in front. Subtract 1 from the power. Do that again. And then the derivative of 6, of course, is not 6. It's 0. We need our second derivative. Bring the power in front. Negative 1.2 x plus 6. We want to find when this is 0 or undefined. It's never undefined, right? There's no dividing by 0. So let's just find when it's 0. And so this is 0 when x equals 5. So this, if there is a point of diminishing returns, it occurs at x equals 5. We need to check if this is actually a point of diminishing returns. And so what we do is we take our number line, we break it up at 5, and we have test values. Let's do 4 and 6. P double prime of 4, if we sub in 4, we get a positive value. And P double prime of 6 is negative. So we go from concave up to concave down. So the point of diminishing returns has an x value of 5. How do we get the y value? Well, we get the y value by just subbing it into our original equation. All right, so subbing in 5 for x, we get a value of 56. Okay, and so this is the point of diminishing returns. In the year that corresponds to 5, I didn't give you any context for this question, but let's suppose this was like years after 2000. So in 2005, our profit is 56, and this is the point of diminishing returns. At that point, our rate of increase of the profit starts to slow down. Okay, and so what I want us to do now is put our first derivative information together with our second derivative information and basically sketch a perfect graph. Okay, so this is a little cheat sheet for how concavity and increasing and decreasing combine. So you start by drawing a circle. I know you're all going to think, oh, this is a unit circle. I hate the unit circle. It's not. It has nothing to do with a unit circle. It's just a circle. Okay? In this quadrant, in this first quadrant, our graph is decreasing and concave down. Okay? So if our graph is decreasing and concave down, it looks like this first quadrant of the circle. In this quadrant, our graph is increasing and concave down. So if our graph is increasing and concave down, it looks like this chunk of the circle. Decreasing, concave up, and increasing, concave up. All right, so we're going to find when our graph is increasing, when it's decreasing, when it's concave up, when it's concave down, and putting all of that together, we're going to use these sections to get a sense of what our graph actually looks like. Okay, so let's do one big example of finding relative max, mins, points of inflection, and sketching the graph. So let's find the relative maxima and minima and points of inflection of the function f of x equals 3x to the fourth minus 4x to the third minus 2. Okay, once we have our relative max, mins, and points of inflection, let's sketch the graph. Okay, so what we need is we're going to find when the derivative is 0, right? Those are the candidates for the max and the mins. And we're also going to need to find when the second derivative is 0, because those are the candidates for the point of inflection. From there, we're going to break up the number line at each of these values that we found along the way and use a test point in each section of the number line to determine increasing and decreasing, concave up, concave down, and then we'll be able to sketch the graph. All right, so we need two derivatives. F prime of x is 12x to the third minus 12x squared. Okay, we want to figure out when this is 0 or undefined. It's never undefined in this example. There's no denominator. All right, this factors to 12x squared times x minus 1. So this gives us x equals 0 or 1. These are the candidates for where a max or a min could occur. Let's turn these into points. So f of 0 is -2. F of 1 is -3. OK, so we have these 2 points. These are candidates for a max or min. We now need the second derivative and find when the second derivative is 0. So I'll just do that here. So f double prime is 36x squared minus 24x. We could factor out a 12x. And we're left with 3x minus 2. Again, we want to set that equal to 0, and that gives us x equals 0 or 2/3. All right, we already have the point corresponding to 0. We do need the point corresponding to 2/3 for when we go to our graph. So subbing in 2/3 into our original function, we get the value. You could just trust me on this one. You get the value of -70 over 27. All right, so that's close to like -4. Sorry, close to -3. It's not very close to -4. Close to -3. OK, and so what we're going to do now is we're going to take our number line, and we're going to break it up at all of these values that we found along the way. We're going to break it up at 0. We're going to break it up at 1. We've already said 0. And we're going to break it up at 2/3. All right, and we need a test value in each of these sections. So for test values, we need something smaller than 0. How's -1 sound? We need something between 0 and 2/3. How about 0.1? And we need something between 2/3 and 1. So how about 0.9? And something bigger than 1. So how about 2? All right, and at each of these test values, we're going to check, is the derivative positive? Is the derivative negative? Is the second derivative positive? Is the second derivative negative? All right, so we're going to have f prime of -1. That's a positive times a negative. F double prime of -1. That's a negative times a negative. All right, so on this section, we are decreasing and concave up. What does decreasing and concave up look like? It looks like this section of the circle. We got to do this for every single one of our test values. F prime of 0.1. That's a positive times a negative. A positive times a negative is a negative. F double prime of 0.1. That's a positive times a negative. That's a negative. So we are decreasing and concave down. Decreasing, concave down. That's this section of the circle. All right, let's do the same thing with point 9. F prime of point 9. That's a positive times a negative. F double prime of point 9. That's a positive times a positive. We're decreasing and concave up. We've already seen that. That's this shape here. And then finally, with 2, F prime of 2 is a positive times a positive. That's a positive. And F double prime of 2 is a positive times a positive. That's a positive. We are increasing and concave up. All right, we're ready to sketch our graph. Let's plot all the points that we found along the way. So 0, -2. I'll label these later or at the end. Our scale, it doesn't have to be perfect. 2/3, negative, close to -3. And 1, -3. So here's 1. Okay, and so from -infinity to 0, our curve looks like this. From 0 to 2/3, our curve looks like this. We also have our first derivative is 0. So we have a flat point there for a moment, and then it goes down. Then we have this shape, and then we have this shape. All right, so let's make sure our points of interest are nice and clear. And let's label them. This is the point 0, -2. And it is a point of inflection. Right, you can see at this point we go from concave up to concave down. That means we have a point of inflection. This next point, and it is not a max and it's not a min, right? Because we go from decreasing to decreasing. So that means it's neither max nor min. And you can see it's not, it's right, smaller than the things on the left is bigger than the things on the right. So it's not a max nor a min. This next point, which is 2/3 -70/27, we go from concave down to concave up. So that is a point of inflection. And this last point, which is -1, -3, sorry, 1, -3, the concavity doesn't change. So it's not a point of inflection, but we go from decreasing to increasing, which means we have a relative min. Okay, so with the first derivative and second derivative, we could get a sketch of a graph that tells us not just when we're increasing and decreasing, but how our curve is bending. So it's almost all of the information that you could kind of visualize from a graph we get from the first and second derivative. Okay, well, I hope you enjoyed this lecture, and thanks for watching these videos. Bye-bye.